All right. So this is the problem we have here based on longitudinal characteristics equation. The quartic means power 4 of quartic of longitudinal dynamic of an airplane is given as the quartic of longitudinal dynamic of an airplane is given as the equation is, see, lambda square plus lambda square plus 5.0159 lambda plus 12.984, one bracket, another bracket is lambda square 0.03406 lambda plus 0.0454 equal to 0. Actually, it will be uh, power 4 equation, and this, if you compare later on, if it is required, you can compare. So it is what, lambda to power 4. Okay, this equation is what is standard pattern for this equation is nothing but a lambda to power 4, b lambda to power 3, c lambda to power d, c lambda to power 2, d lambda plus d. This is the actual pattern, and this is basically the characteristics equation or stability equation, and it will be given in this format always. Okay, and based on the Routh's criteria, like last class we had discussed and we had seen also, so that we will use here. Okay, now coming to the solution of this coming to the problem of this uh, uh, exact what they are asking in this problem. See, the question will be given like this, and now see what data they are asking. They are asking calculate calculate the time period time to half, number of cycles number of cycles to half, identify the modes and compute the damping factor and natural frequency of the. This is the question. Now you go for the solution of this problem. It's very easy. Last lecture I had given the formula how to get the value of time period, how to get the value of time to half, okay, number of cycle to half. This all I had given last lecture, so I will write the formula, so you have to remember the formula only, that's all. Okay, now coming to this solution for this problem. So what is the equation we have? If you check, This equation is, I would write like this. Now solution we are going to talk here. Okay. So this is nothing but lambda square 5.0159. Okay. Lambda plus 12.984 lambda square 0.03406 lambda plus 0.0454 equal to, what you can do, simple concept, you have to use one bracket will equal to 0, and in the same way another bracket also will be 0, because the product is becomes 0, so you don't know which one is equal to 0, which bracket is 0, or so simple mathematics you have to use for the solution of this. You just make first bracket lambda square 5.015 lambda plus 12.984 is equal to 0. Okay, this is nothing but equation 1. And same thing you can do for the other bracket, which is nothing but lambda square 0.03406 lambda plus 0.0454 is equal to 0. So immediately what you will try to do, you just find out the root of this equation 1 and 2. So from equation 1, if you solve the equation 1, then obviously this is the quadratic equation. So from equation 1, what is the equation 1? We have lambda square 5.0159 lambda plus 12.984 equal to 0. If you solve this quadratic equation, so root you may get like this. Lambda 1 you will get here. It will be minus 2.508. Okay. And plus I complex value you will get 2.587, and similarly you will get lambda 2 minus 2.508 minus I, that is imaginary part, 2.587. So ultimately if you check the roots lambda 1 2, you will have minus 2.508 plus minus I plus minus I 2.587. If you have gone through the complex number chapter in engineering mathematics, so quadratic equation will be there, but sometimes you will get the complex value, means real and imaginary both. So how to write real and imaginary in complex number? It is format x plus iy. So x is nothing but real part and y is nothing but imaginary part, which is denoted by q. Last lecture I had discussed about r and q, or p and q something. Huh? It was explained by p and q. Okay, last class I had discussed this. So this is p and q. So p will be what? Real value. This is real, and this value will be imaginary. Okay. So, but don't worry this much, because I told you this problem you are here solving, but in examination directly they will give root. They will give this type of root. Okay, so they will not give so much complication in the calculation point of view. They simply just want to know you know the concept or not. Concept for what? Like how to get the damping factor, how to get the damping ratio, how to get the natural frequency, how to check what is the mode of the oscillation. I mean, it is short period oscillation or it is long period oscillation. So that concept they want to know. They are not going to check your calculation actually here in this case, because if you go for the calculation point of view, so segregate the equation to get the roots, it's very time taken. So don't worry, in examination they will give the roots. Okay, so like here you got this roots lambda 1 and lambda 2. You can write lambda 1 2, which is nothing but plus minus format. Now one is plus root, another is a negative root. So combined you can write plus minus this. So this is the root now. Okay, similarly from equation 2 also here you have to check. Similarly from equation 2, if you check what is the equation 2, here you have written lambda square. It's nothing but lambda square it's lambda square 0.03406 lambda plus 0.054 equal to 0. So again, this is the quadratic equation. If you check the root for this equation also, so what will be the roots? Simple. Again, I can say this is now lambda 3 because 1 and 2 already we have taken. So I can write lambda 3 is equal to minus 0.017. Once you solve this quadratic equation, you will get like this. Plus imaginary part is nothing but 0.2125, and similarly lambda 4, if you check, it is 0.017 minus of I imaginary part 0.2125, or you can say, you can write like this, lambda 3 comma 4 means two roots you got from this equation, that is nothing but 0.017 plus minus imaginary part is nothing but 0.2125. This two roots, you got two roots here. Okay, how many roots? Two roots here, no? Lambda 3 and lambda 4. And how many roots here? Again you got two roots. Okay, two roots here also you got. So total four roots obviously you will have, because if you check this equation, one bracket here and another bracket is here, and this is lambda square, this is lambda square. Once you open the equation, you will get the standard format. What is the standard format? This is the standard format, means lambda power 4 terms you may get. Okay, so lambda to power 4 format you may get, that is the characteristics equation for the longitudinal dynamic stability. Okay, so it is very clear, if power is what 4, then four roots you may have, like lambda 1, lambda 2, lambda 3, lambda 4, four roots. Now you have two roots. Okay, two roots pair you have. Now if you check in this problem, uh, for all four roots, okay, I mean, if you check lambda 1 2 and lambda 3 4, both roots, if you check, we are having a imaginary or complex roots basically, huh? Roots are complex, and if roots are complex, and if real part are negative, then what it will represent? It will represent damping oscillatory motion, that I had given last class. This was the notes I had given for the Routh criteria. If you check the previous class notes, you will understand, but here again I will write in notes, so those who were not available last lecture, so here they will understand. If 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 roots are complex, like here roots are complex, if roots are complex with with negative with negative real with negative real part with a negative real part, it represents it represents damped oscillation. Always remember this condition I had given last class. Okay, damped oscillatory, okay, represents damped oscillatory motion. Damped oscillatory motion. Okay, represents damped oscillatory motion. You just make a note, because this one I had given last lecture. It's a Routh criteria basically. So if you check all roots, what we are getting here, it's complex, because if you check the format, it is x plus minus iy. This is what complex. Okay, x plus iy, it's complex number you have gone through in engineering mathematics. So it is complex, basically complex function x plus iy, complex function pattern basically x plus iy. So if you check here, all roots are imaginary. That one condition is what all roots are complex. It is now satisfied. Now check the real part. Which one is the real part? Just now I have told you. If the first part is what real, and second part is what imaginary, because it is with I a symbol, so it shows that whatever the component with I, that will be the imaginary component. So check real component, it is minus. See, this is the minus here also, and the same thing here also we are getting negative real part. So if negative real part we have, then it will be the damped oscillatory motion. Okay, till now I have not discussed about vibration or in free vibration, force vibration. That chapter we had not done, but I believe that basic idea you may have. So if you have uh, damped oscillatory motion, so there is the standard pattern for the damped oscillatory motion. Okay, what is that? I'll write here. That is nothing but damped oscillatory motion. Damped oscillatory motion. What is that? It's nothing but it's nothing but minus chi omega n plus minus I in bracket 1 minus chi square into omega n. So here also if you check, this is also, this part is nothing but real part, see, and this part is nothing but imaginary part. So whenever you will have a damped oscillatory motions in vibration, we will derive that. Okay, and it is this is the equation basically. So we'll derive it in vibration. So this is the equation when there is the damped oscillation. So basically with the help of this, we are taking this one reference uh, equation for damped oscillatory motion, and we have to compare this from our actual equation. Okay, now one more thing you need to know, like whatever the value here we have, like uh, in this equation, this chi, so chi and omega n, you know it is natural frequency, and chi is nothing but the damping ratio. It is called damping ratio. Okay, if you want you can write also, chi is nothing but damping ratio. It is called damping ratio, and omega n, obviously it is the natural frequency. Natural frequency in radian per second. Okay, and one more term I just want to use, uh, omega d. Omega d is called damping frequency in radian per second. Okay, so what is the damping frequency omega d? That formula you need to know. Omega d is nothing but, what is the imaginary part? That is called 1 minus root 1 minus chi square omega n. So this part called a combined part, root 1 minus chi square omega n, this part called as a WD, which is nothing but damping frequency. Okay, so you just remember here, because we are comparing, because everything now I have explained, oscillation will be there in dynamic stability. So now we are comparing with the vibration, because in vibration also we have a damped oscillation, undamped oscillation. So here, if you check the damped oscillation final equation in vibration, this you may get, and you may remember also, if you check, remind it, then you may get, this was the equation for the damped oscillatory motion, underdamped, basically underdamped. Okay, it is also called underdamped. Underdamped. All right. Now we have to simply compare this. Now, coming to the problem, what is the problem? Actually, in the problem, what they said, calculate the time period, time to half, number of cycle to half, identify the modes, and compute the damping factor and natural frequency. Okay. Now, if you see here, in this case, two types of the motion you have: short period oscillation and long period oscillation. So for both, one by one will do. You have to check, because till now whatever I have explained, long time period oscillation called phugoid, short time period oscillation called uh, short time period oscillation. It was explained like, if the time period is what? very small, means natural frequency is very high, so it will be called a short period oscillation, right? And long period oscillation means time period is very high, so obviously natural frequency will be very less. So based on that, we have to analyze. So now two type the motion we have, and now we are going to check one by one. Two roots we have here, lambda 3 4, I can consider this is the one combination of roots, and lambda 1 and 2 combination of roots we have. You just write and check which one is the long period oscillation and which one is the short period oscillation. I expect my expectation to all of you, you have to tell me which one is the long period oscillation and which one is the short period oscillation. I just want to write the couple of root. First couple of root is nothing but, like you had calculated from the equation 1, it was minus 2.508, okay, plus minus imaginary part 0.2125. This is the one couple of roots, and another couple of roots are 3 4, which is nothing but, if you check, it was minus 0.017 plus minus imaginary part 0. Sorry, that part was 2.587. You want to, if you check, let me correct this, 2.587 imaginary part. See, imaginary part 2.1587, imaginary part for 1 2 roots. So what is the value here? See, now it's nothing but 2 point, imaginary part 2.587, and for this imaginary part was 0.2125. Now two couples of roots we have. This is the one couple of roots, and this is the another couple of roots. This is, I can say, A, and this is B. So if you have to check, and if you are not able to understand, it's very clear, simple, you can understand. You just compare these roots with your standard one, and from there you will get which one have a higher natural frequency, because if higher natural frequency will be there, then time period will be less. That I already have explained. Okay, if you check natural frequency and time period oscillation formula, so omega n is nothing but 2 pi t. This was the formula. So natural frequency and time period is what? Just opposite. So if it is the a long time period oscillation, it means it will have a less frequency, less natural frequency, and just vice versa, right? And just vice versa. If it is short time period oscillation, it means it will have a high natural frequency. Now you can compare, and how you will compare? It's very simple. Check the coefficient. Okay, check the coefficients. Anyone you can take, like this value, first one. So this is the real part and this is the imaginary part. Okay, and obviously here also this is the real part and this is the imaginary part. So check your standard equation from here, minus xi omega n plus minus 1 minus xi square omega n, right? If you check root 1 minus xi square omega n, also the damping frequency, not natural, damping frequency, and this is minus xi omega n. So from here, if you check the first minus xi omega n is what? Higher value. So obviously omega n will also higher, and this minus xi omega n, if this real part is small, it means omega n is what? Small. If omega n is small, it means time period is high. If time period high, it means it becomes long period oscillation. Now two roots you have checked. See the first real part, this is what the real part, and this is the imaginary part. Okay, R and Q, you can say. So real part, if you check, this is high. If real part is high, it means natural frequency will be high, because first real part we have natural frequency here. Okay, we have natural frequency here. So if first real part is what? High, it means natural frequency is high. It means time period is basically less. If time period is less, it means it becomes a short period oscillation. So can we say this lambda 1 2, it is now clear, lambda 1 comma 2, it is the short period oscillation. Now coming to the, this one is clear, okay? Lambda 3 4, see, the real part is very small, real part is very small. If real part is small, check your standard equation, real part is small, it means omega n will be less. If omega n is less, okay, if omega n is less, it means time period is high. If time period is high, means it becomes long period oscillation. So you got that lambda 3 4, this root is nothing but long period oscillation. Okay, long period oscillation also called as cuboid. You know that, right? So first calculation you have to perform for the short period oscillation. And one more thing you can understand, if it's a short period oscillation, then why it will be the short period oscillation? If short period oscillation, then why it is short period? It means you can say that that oscillation will have a very higher damping value. Damping means what? Damping is basically defined to continuous reduction of amplitude. And if it is short period oscillation, if it is short period oscillation, it means damping is very high. For that reason, oscillation is what? Very short, short period oscillation. Okay, so short period oscillation means very high damping ratio. So in that way also you can say the real part will be very high if damping ratio is high. In that way also you can understand. Okay, it's your choice. You can relate with the natural frequency or with damping ratio. Because in real part, if you see, we have a damping ratio also, J. So if J is very high, it means damping ratio is high, and damping ratio high means it will have a less or short time period oscillation. So in that way also you can understand. Otherwise, with natural frequency you can understand. It's your choice. Okay. So if you see where damping ratio is very high, damping ratio is high in this first equation. So it means it is the short time period oscillation. In which damping ratio is very less in second roots. See, damping ratio is real part, we have a damping ratio right here. If you check, the real part is very small, it means damping ratio is very small. If damping ratio is very small, means yeah, it is not trying to damp out, then it means it will have a long period oscillation. So it's your choice. You can relate with the natural frequency or with damping ratio. In both way I have explained. But now onward, you understood lambda 1 2 roots are for the short period oscillation and lambda 3 4 roots are for the long period oscillation. Now we'll take one by one. First we'll start from the lambda 1 2 roots. Lambda 1 2, which is representing short period oscillatory motion, oscillatory motion. Okay. Now for this we are going to calculate, what we are going to calculate, the all value. Here it is said what value they are asking for that. They are asking calculate time period, time to half, number of cycle to half. Okay, so the, and identify the modes. So modes we have identify short period oscillation and long period oscillation are the modes. So modes is identify now. Now we are going to compute the damping factor or damping ratio also sometimes called, and natural frequency of the modes. Both we are going to find out. Okay. So let us see. First we are going to take short period oscillation lambda 1 2, and this lambda 1 2 is nothing but, if you check here, lambda 1 2 is nothing but what we have, it's a minus 2.50, 2.508 plus minus, it's a imaginary value 2.587. So with our standard equation we have to compare that roots lambda, that's roots was it was, this is the actually here, this is the standard equation, but this is the roots value. Okay, lambda, I forgot to write, but now lambda is nothing but minus j omega n plus minus 1 minus j square in root imaginary part, and then it is omega n. So we have to compare with this. Once you compare, then you will get the value. What it is, check. You will have a minus Xi omega n is equal to minus 2.508. This is equation number 1. Second equation you have 1 minus xi square omega n is equal to 2.587. This will be the equation. Okay, this will be the equation. Now this equation you have to use, and you just calculate the value of xi and omega n separately. This is the second. You just compared. Okay, the standard equation you have compared. You take the ratio omega and omega n will be cancel out, and xi value you have to calculate. Once you calculate this xi value, then what xi value you will have? Chi value is nothing but the damping factor or damping ratio. Okay, damping factor or damping ratio, and this is nothing but first you will calculate, and you will get 0.6961. This is the Chi value, and if you get Chi value, put in any equation, then omega n you will have, and what will be the omega n? It will be 3.6029 radian per second. I have calculated, so I am giving. It will little bit. It will take time, but you can do it. Okay, so this is the xi value from this equation 1 and 2, and this is the omega n. What they had asked damping ratio or damping factor also called. Okay, so xi they had asked, and you have calculated. Okay, right. Xi is also called damping ratio or damping factor. There should not be any confusion. All right. Now coming to the this is the first one you have done, which is for the short period oscillation. The same thing you can do for the uh, long period oscillation, but before that, as I told you, we have to calculate the data for the short period oscillation. What are the data? Data are like, they are asking the time period, time to half, number of cycles. So we have to do this because we have calculated this damping factor and natural frequency for short period oscillation. Modes is what defined. Modes means short period or long period, so it is short period. Damping factor, which is also called damping ratio, and natural frequency you have calculated. Now we are going to calculate time period, time to half, number of cycles. Three value we have to calculate back to back for short period oscillation. So now for the short period oscillation, we are calculating it. Okay. Short period oscillation. What we are going to calculate first? We are going to calculate time period. So time period formula I had given, if you remember, time period. Okay. So if you remember the formula for the short period, I had given 2 pi. Okay, if you check, it was 2 pi t cap, 2 pi t cap divided by q, divided by q. Q was the imaginary value. Okay, q was the imaginary value. It was explained in last lecture. So we have 2 pi t cap, and q is nothing but, for this just now we have seen, it is 2.587. 2.587. This is the time period for the short period oscillation. Okay, now if you go and calculate the value of uh, uh, time period for the phugoid, or first we'll finish the time period for the this one, uh, short period oscillation only. So time to half. Okay, time to half for the short period oscillations, it was denoted t1 by 2. If t1 by 2, if you go and calculate for the short period oscillation, so it was explained, it will be 0.693. This all formula I had given last lecture. Okay, divided by P or R, I will say. I think in last lecture I had explained P. So P or R is a real part. Okay, Q was imaginary and R was real part. So it's nothing but how much you may have, 0.693 T divided by R. R is the real part, and what is that value? It's a 2.508. It's a 2.508. Okay? 2.508, and obviously it's a minus value, so minus is here and minus is here, so it will be cancelled out. So I will write 2.50. You have to solve this. Then time to half T1 by 2, it is for what? Short period oscillation, SPO. If you calculate 0.693 divided by 2.508, so it is almost 0.2763 T cap. And I explain you what is the T cap also. Okay, that value I had given, but mass and velocity they have not given, density they have not given. So T you keep as it is. Okay, T you keep as it is, and this is the time period you have calculated. Okay, time period, if you solve this 2 pi and 2.587, if you calculate this value, so ultimately what you will get, 2.428 T cap. So T cap, actually it's also the one function in terms of mass, in terms of density, in terms of velocity, but they had not given, so you just keep that value in terms of T1. This is the what, time to half, and another is we have to calculate number of cycle to half. Okay, so number of cycle to half is denoted by n1 by 2. And if you remember the formula, what was the formula for the number of cycle to half? It was fn natural frequency into time to half. Okay, time to half. uh, so time to half T1 by 2, just now here you have calculated, it's a 0.2763 T cap. Fn is the natural frequency, and you have to calculate this value. What is the natural frequency? It is omega n by 2 pi into T half is nothing but, just now you have calculated, 0.2763 T cap. If you see the n half, number of cycle to half for the short period oscillation, SPO, just now here you have calculated omega n. What is the omega n for the short period oscillation? Here you have written 3.60. See this value, 3.6.
3.6.
Right, right. 3 point,
6029.
right. 3.6029 divided by 2 pi into time to half is 0.2763 in terms of T cap. Okay. Once you solve this, so you may have n by n half, that is number of cycle to half for the SPO, for the short period oscillation, you will get 0.1584 T cap. Remember, T cap is also a function. Okay, so once detail of the airplane they have given, like mass, density, velocity, and all those things they have given, then T cap also you can write the value, but it is not given, so you can keep this in the same function. All right, this is done. All three value you have calculated, uh, time period you have calculated, time to half you have calculated, and number of cycle to half you have calculated, but this is for the short period oscillation. The same thing you have to perform for the long period oscillation. So if you go for the long period oscillation, okay, second one, long period oscillation, which is also called, you go ahead. Okay, now for the long period, and have patience, because I told you this is very conceptual thing, and question they are asking in exam multiple time they have asked. But whatever the lengthy problem I am solving here, such type of lengthy problem they are not asking. They are giving all the data to you, and simply they are asking what is the damping ratio, what is the natural frequency, or they are asking the mode of the oscillation, like it is short period or long period. That's all. So I mean, if you understood the whole concept, like this problem, if you nicely, if you understand, then exam problem within 2 minutes you can solve, and after this we'll solve the gate problem. So for that reason I'm saying you have to be patient. Okay, and just with follow me each and every steps. you got any confusion at any steps, any doubt you are getting, immediately you can interrupt and you can ask me. Calculation values I'm filling from my side, because if you ask you to calculate, then it will take so much time to complete this problem, because literally this is very lengthy problem. Okay, so we just have patience and just watch it nicely and just follow all the steps. Till now what calculation we have done, it was for the short period. So how we have started for the short period, we had written the roots. So now the same steps we have to follow for the long period oscillation also. So long period oscillation, what are the roots? We have lambda 3 and 4. And if you check for the long period oscillation, so it was minus 0.017 plus minus imaginary, it was 0.2125. Again we have to compare, we have the root, it is nothing but xi omega n plus minus I root of 1 minus xi square, okay, into omega n. Again we have to compare the same thing we have to do, just like for the short period oscillations, we will have a xi omega l is equal to minus of 0.017, make it equation number 1. Similarly you can take any value, like what we have, it is root of 1 minus xi square omega n, and it is nothing but take plus 1, so 0.2125, this is equation number 2. Okay, you just solve equation 1 and 2, then you will have xi and omega n. So what is the xi? That is the damping ratio. After comparing this, you may get and solve equation 1 and 2. Take the uh, division, omega n and cancel out. So xi you will get finally. What is the value? It is nothing but 0.0798. And again, once you got xi, then keep it in equation 1 or 2, then you will get omega n, and this value is nothing but 0.213 radian per second. So these two values are very important, because they had asked in problem calculate damping factor and natural frequency. So this is the damping, and in gate this value they are asking. Many times they had asked this value only. They ask simply what is the damping ratio and what is the natural frequency. Sometimes they will ask the damping frequency also. So damping frequency, I told you, this value is nothing but damping frequency omega d. So omega d is nothing but 1 minus xi square omega n. All right, coming to the next, like again you have to calculate the time period for the phugoid. So what is the time period for the phugoid motion? Okay, time period. Okay, we are calculating time period. So the same formula, just like a short period oscillation, what is the time period for the phugoid? So same thing we can say, it is 2 pi t cap divided by, I told you, you have to write the imaginary part here. So imaginary part is denoted by q. So you just keep this value. It is nothing but 2 pi t cap divided by what is the imaginary part here? It's nothing but 0.2125. 0.2125. If you solve, then what value you will have? You may have 29.56 t cap,
Five
almost this value.
six.
Yes. Now what value you have to calculate? The next you are going to calculate the time period to half. Okay, so you are going to calculate time period to half, or simply you can say time to half. So it will be denoted by t1 by 2, and this is for phugoid, so you can keep ph here, so it will be clear. Okay, so what is the time period for the phugoid? So I told you the formulas for the short period oscillation also the same. Here also you have to write t cap divided by, you have to write the real part. So real part is denoted by suppose r, so minus 0.693 t cap divided by, what is the real part? If you check, it's nothing but minus of 0.017, right? So just cancel out something, you will have, so ultimately what you will get for the phugoid, it's nothing but 40.7 t cap. You can see the long period oscillation, see what is the time period, you are getting 29, and short period oscillation, see you the time period you will understand what is the short period oscillation. It is 2.42. So 2.42, and this is what 29 points. So it's a big. That's the reason it is called long period oscillation, and that one is called short period oscillation. All right. Now the same you can calculate for number of cycle to half. So what is the number of cycle? Number of cycle to half is nothing but n 1 by 2. And if you remember the formula I had given for this, it was fn into t1 half. What is the fn? It is omega n by 2 pi, and t half obviously 1 by 2. Just now you have calculated, and 1 by 2 means number of cycle to half is fn. Fn is omega n by 2, and what is the omega n? Just now you have calculated, it's a 0.213. You just keep this value 213 divided by 2 pi into time to half is nothing but 40.7, and this is t cap. Okay, if you solve this, then number of cycle uh, to half for the figured motion is approximate 1.381 t cap. This is the this part is what done. Okay, this part is one done. This problem is done. I told you one problem we have to solve, which is the ask in gate. So multiple problem they have asked actually, but one problem will try at least based on this. Okay, it's very simple. So